In this video, we're continuing section 3.2 on the graph of a function, and we're going to focus on how we sketch simple graphs that have holes. So I'm going to get right into an example where we got to sketch a curve, find the domain of the range, and then find any relevant points, things like an intercept or a vertex, or as we'll later see, a hole. I want to find all such points and label them. Okay, so I got this function, this fractional thing. The technical word for a function like this, when I have a polynomial divided by another polynomial, is what's called a rational function. Rational function. Okay, so one thing I might notice about this is that the numerator can be factored. So let's first factor it. So I'll get x and an x. My denominator is x minus 2. So how does it factor? I need two numbers that add to negative 8 and multiply to 12. And that's going to be minus 2 and minus 6. And now that's nice because I can cancel the x minus 2's. So that leaves me with x minus 6. Okay, so one very important thing that I need to include is whenever there's something like this in the denominator that cancels away. More generally, if there's a domain restriction that cancels away. And that's happening because, well, what if the denominator was 0? I can no longer see that's a problem in my final simplified answer. So there was a problem here if if x was 2. Because if x is 2, the denominator of my original thing is 0, and that makes it undefined. So I need to specifically include that in my final answer and say that, wait, comma, x cannot be equal to 2. I need to remember that domain restriction. If I don't have that domain restriction and I just say it's x minus 6, well, that has a different domain than the original. And that's going to make the function different because the x values are going to be different. Okay, so how do I graph something like this that has a domain restriction? First, let me just graph y equals x minus 6 as if there was no domain restriction. Because we know that that's a graph, that's a line. The y-intercept is at negative 6, and it's got a slope of 1, so it's upward sloping. Upward sloping. Okay, so my graph of y equals x minus 6 looks something like that. So now, well, how do I modify that to get the graph of y equals x minus 6, comma, x is not equal to 2? So if I include this domain restriction, how does it change the graph? Well, essentially, I'm going to have this same graph shape, but I have to skip the point when x equals 2. So let's first find the point on the graph when x equals 2. So if I were to plug in 2 for the x, in here I get y equals 2 minus 6, which is negative 4. So when x is 2, the y coordinate is negative 4. I need to skip that point when I get to that point on the graph. So my graph is still going to go through that same y-intercept. Still going to go through that y-intercept, and now let me label the whole point 0, comma, negative 6. But once I get to this point, 2, comma, 4, I have to skip it, and that makes a whole, sorry, that should be 2, comma, negative 4. I have to skip it, and that creates a hole in the graph. And then I continue onwards, and I draw the rest of my line. Okay. All right. So what's left to find about this graph? I got the y-intercept, but I don't have the x-intercept yet, so let's get that. X-intercept. To find an x-intercept, I set y equal to 0. So get 0 equals x minus 6. So then x equals 6. So my x-intercept, let's label it, is 6, comma, 0. That's my x-intercept. I got my y-intercept already. And I got the coordinates of the hole, so let me label that as well. So that is the hole. I got the x-intercept. The y-intercept, let's label that as well. Y-intercept was this, 0, comma, negative 6. Okay, what else did it want? Domain and range. So let's get those. All right, D for domain. Well, domain is, looking at the graph, it's everything except I skipped the x value 2. I can also see that from this domain restriction. X can't be 2. I can also see it from the original formula. I'm allowed to plug in everything except what makes the denominator 0, and that's 2. So domain is negative infinity, parentheses, up until 2, parentheses, union 2 onwards to infinity. And then for my range, the y values, Well, the y values could be everything, except there's one y value that gets skipped, and that happens to be the y coordinate of the hole. So negative infinity up until negative 4, union, parentheses, negative 4 onwards to infinity. Okay, so now I have everything. I got the graph, I got those relevant points like the intercepts and the hole labeled, and I have my domain and range. Okay, let's do one more example. One more example here. I got a more complicated looking function. All right, but I noticed that with this one, part of it's already factored for me, and I can cancel x minus 1 on the top and on the bottom. And doing that, I'm left with x squared minus 8x plus 12. But remember, there's this domain restriction from the denominator that canceled away. So I need to explicitly write that in at the end. So x was not allowed to equal 1 in the original function. So even in the simplified form, x better not be equal to 1. I need to skip that x value. I need to remember that. Okay. So, well, let's focus on this simplified graph. Oh, that's a quadratic. Oh, so I know it's going to have a parabola graph. And to be able to draw its graph more precisely, let's get its vertex. So let's put this thing in vertex form by completing the square. So I'm going to take this coefficient of x, which is negative 8. Let's divide it by 2, which gives me negative 4. And then I got to square that. So I got to take negative 4 and I got to square that whole thing. And that gives me 16. Okay, so when I complete the square, I get y equals x squared minus 8x. I'm going to leave some space now and then write plus 12. And then I take this number that I got and I will add it first after those x terms, the x squared and the x term. And then because I added it, I also have to subtract it on that same side. Because if I add 16 and I subtract 16, well, it's like overall a net, I added 0. And that doesn't change the value of my original thing, which is very important. Okay, so now recall that when I do this, these first 3 terms should factor perfectly. I'll get y equals, as a perfect square, I'll get x and then something squared, and then 12 minus 16 at the end becomes minus 4. So I could definitely factor this. It's not too bad, and it factors as x minus 4 squared. But remember also the shortcut for getting this number. The shortcut is the number that goes here should always be, that number should always be what I get when I divided my b coefficient by 2, which was negative 4. Those should always match up. All right, so this is now in vertex form. So we are ready to write the vertex. Vertex, the x coordinate is 4. Right, it's what I plug in here to make that 0. And if I do plug that in, well, then the y value becomes 0 minus 4, so which is negative 4. So my vertex is 4 comma negative 4. Okay, so I got some info about the graph. The vertex is at 4 comma negative 4, 4 comma negative 4. But to get a better sense of the graph, I need my intercepts. In fact, the problem specifically asked me to get some intercepts. So y-intercept and x-intercept. For my y-intercept, I plug in 0 for the x. And I think it's going to be easiest to do that if I plug it in to this form before I completed the square. So that'll give me x. If I plug in 0 for x, I'll get 0 minus 0 plus 12. Well, that's just 12. So I know my y-intercept's at 12. Let's get the x-intercepts. For my x-intercepts, I plug in 0 for the y. I could either do that in this original form or in the completed the square form. But I noticed that we had factored this quadratic in part A. So let's do it in that original step. If I plug in 0 for the y, let's use the fact that we had factored this because it factors as x minus 2 times x minus 6. Oh, okay, so now I know that x is either 2 or x is 6. So let's label my x-intercepts. There's one at 2, there's one at 6. And that makes sense because the vertex x-coordinate is halfway between those two numbers, the 2 and the 6. So now if I draw my parabola, I know it's upward facing because the leading coefficient in front of this x squared is a 1. So it's upward facing, goes through that x-intercept at 2. Then it keeps on rising Okay, let's label the y-intercept. Well, the y-intercept is at 12 here. Okay, the y-intercept is going at 12. Okay, so that's what the graph would be if I was just looking at y equals x squared minus 8x plus 12, but without this domain restriction. Now let's throw the domain restriction in there. So y equals x squared minus 8x plus 12, comma, x is not equal to 1. Okay, so overall I'm going to have the same sort of general shape of the graph. Vertex is at 4, -4. Then it starts to rise like this. This point right here, this x-intercept is at 2, 0. Going the other way, this x-intercept is at 6, 0. And if I keep going like this, I'll keep going up and up and up. But once I reach the x-coordinate 1, that's the x value I have to skip. So when I skip it, that's going to create a hole in the graph. And then I just continue on with the rest of my parabola. All right, and let's label the y-intercept. That one I can label. That was 0, 12. So, well, I know the x-coordinate of the hole. For the hole, I know the x-coordinate is 1, but what's the y-coordinate? So to get that, I can plug it into this formula. I can plug it into that formula. It gives me y equals, plug in 1 for the x, 1 minus 8 plus 12. So that's going to be 5. So the y-coordinate of the hole is 5. Okay, so at this point I have the hole. We got our y-intercept. We got the x-intercepts. There's 2 of them, x-intercepts. There's this, and there's this at 2, 0. And we have this vertex at 4, -4. I'm labeling it. All right, and then the problem asks me for the domain and the range. So for my domain, for my x values, well, x can be everything, except where the hole is, x cannot be 1. So domain is -infinity to 1, parentheses, union 1 to infinity, parentheses at the 1 again. It's not included. What about for the range? For the range, I want to have you try that on your own first. For the range, take a quick pause, 30 seconds. Try to write down the range. 4, 3, 2, 1. Quick pause. Try to write the range. All right, let's talk about it. Let's talk about the range. So the smallest the y values get is at the vertex. The y-coordinate is -4. So the range starts at -4. Bracket, because I do attain that y value. There's a closed circle there at that point. So the question I kind of want to ask now is, well, the y values get bigger and bigger and bigger, and they kind of seem to skip the y-coordinate 5, like where the hole is. Like where the hole is, there's that y-coordinate 5. But is 5 actually a part of the range? It turns out yes. Even though there's a hole at that y-coordinate, there's another point on the graph, if I go over here on the other side of the parabola, with that y value 5. So because there is a point somewhere else on the graph with that y value, 5 is very much a part of the range. Okay, so in fact, if I were to look at the whole right-hand part of the parabola, I actually reach all of the y values above this. All the y values above -4, well, we reach every single one of them. So the range is -4 onwards to infinity. And that's my range. So I got the graph, got all the relevant points labeled, got my domain and range. That's my answer.